Hello, everyone, and good morning. My name is Galoran, and I'm with the CS department at the Technion, and with the Scientific Computing Center at the Israel Atomic Energy Commission. And today we are going to talk about the amazing transition that NVRAM has done for HPC and supercomputing, and specifically the transition from theory in this regards to reality. In this research group, we have several people. Specifically, the PIs includes Professor Hagit Atiya and Professor Danny Handler, and several PhD and MSc students. And I will also would like to acknowledge the support that we got by PASI, ISF, Lee and William Frankel Center, Intel, and the Negev HPC project. Several publication in this regard has been published in SC21, 22, ISC 22, and IXPAC 21, 22. So let's start from the beginning. It is clear that HPC systems are critical research for scientific research. No one has any doubt about that. But I think that the other aspect in high-performance computing that we don't often see or think about is memory. And the memory, the extension in memory, is the one that allows increasing the resolution of models that only 2 decades ago, it was unimaginable that we can even simulate. From a galaxy's exploration to Earth and climate research, as well as industry purposes for commerce to clean energy in universities and research centers, in public and private companies, either it's a Mars rover or just your car at the parking lot, in the physical world, or maybe in the new twin cities and infrastructures. We see that the need for large scale and effective high performance computing and memory is growing. And it's actually all around us. But there is a problem, a huge one, with the future of those machines. As those computers grow in scale, and right now they are in the exascale, they also have a lot of complexity that even a small piece of hardware failure out of the tens of millions in there, or even just one hiccup and a hero calculation, one that holds synchronously the entire system, will fail immediately. And for that reason, we do a common checkpoint restart and other fault tolerance techniques. However, in the case of exascale, everything is different. If previously we considered those systems to be somehow reliable, the future is not holding to this promise. And as such, a computation that will constantly need to approach the non-volatile storage over and over again will de facto cause the effectiveness of the computer to drops in orders of magnitude. And after years of projections about this not quite optimistic future, and unfortunately, it was completely true. The new and single exascale system out there, the Frontier supercomputer at Oak Ridge in the US, still cannot run a hero calculation without a crash. And it's been more than 6 months since it was launched. So we clearly observe now that while considering the gaps between the needs of the computation and the given HPC system, three main pillars are most crucial to address in the case of fault tolerance: the computation, the memory, and the storage. And more specifically, the huge gap between their specs, their development over time, the role they play, and the interactions they have with each other. So while we just got into the new and exciting exascale era, with Moore's law keep not breaking in this way or the other, still the common way today to support fault tolerance, even with those enormous sophisticated systems, is by checkpointing the computational state of the program to a storage device and retrieve the last available checkpoint in case of a failure. Now, while it was somehow possible and tolerated in petascale systems, the storage performances are extremely low in comparison to the computational power of those systems, and exhibit no significant improvements in technology over the years. Like HDDs and SSDs, all storage devices create a huge bottleneck to scientific applications, creating a significant gap that scientific computation suffers from. There is also a gap between the storage and main memory in certain aspects, such as the capacities. The DRAM capacity is very limited. However, the main memory introduces better performances than that of the storage in about 2 or 3 orders of magnitude. However, main memory is volatile and cannot serve as persistent storage to applications. Also, the storage cannot serve efficiently as an expansion to the main memory, as its access latencies are extremely high. The DRAM technology made progress over the years, and the common use technology today is the DDR4, introduced a decade ago. The world's first DDR5 DRAM chip was officially launched last year. The next supercomputers are planned to integrate this new hardware. DDR5 has about the same latency as DDR4, but it's targeted to double the bandwidth and reduce power consumption. Overall, not a big change, if to be frank. We can also see clearly that these memory specs in the memory capacity per core over the last decades in the top 500 list, overall, there are only about a few gigabytes per core over all of those years, and the trend remains today. And of course, despite these advances in DRAM technology, DRAM's performances are still low in comparison with the growth of computational power. The DRAM also is expensive and limited in capacity and bandwidth, creating a significant gap with the increasing demand for computational power for high-resolution models. Putting all those concepts in one graph, we say that the storage technology evolves very slowly, introducing very large capacities of non-volatile memory, but with significantly low performances. As we said, 2 to 3 orders of magnitude are between the performances of DRAM and storage devices. The DRAM technology advances over the last decades increases, but its performances are still way behind the computational power increase. So these unbearable gaps brought to the emergence of non-volatile RAM and their integration in the next generation of supercomputing systems. The Aurora supercomputer we mentioned at the beginning, for example, is planning to consist NVRAM. And actually, I just returned from SE conference at Dallas to see the new storage system, their NVRAM NVMe SSD storage system that is already working and ranked #1 on the new IO 500 list with an order of magnitude advantage over other non-volatile RAM enabled systems. So while NVRAM was basically a dream for half a century, the 3D X-Point technology by Intel and Micron made it possible commercially for the first time. The advantages of 3D X-Points includes very low latency, simultaneous read and write operations at very high speeds, very high endurance, and I will give a heads up by saying that other limitations kill it eventually, but let's wait a bit. Now, the Intel Optane was the first product to use this technology, this 3D X-Point technology, in two settings. As a very fast SSD storage only, and in persistent memory, which in the 200 series was also accompanied with a persistent cache due to advances in EADR. As you can see on the pyramid, the persistent memory creates a new tier between the standard storage devices and the volatile memory hardware. DCPMM are priced in accordance with their market position, well above regular SSDs, but well below DDR4 of the same capacity. Persistent memory aims to have memory-like performances, but still there is a certain gap. For example, Optane's bandwidth on write operations is about 8% of that of DRAM. Now, back talking on the Optane can be configured in two modes. The first mode is memory mode, which in this mode, the device acts as volatile system memory under the control of the operating system. So no changes in software are required. It is transparent to applications. Any DRAM in the platform acts as a cache working in conjunction with the device, together creating a large pool of volatile memory. The second mode is UpDirect, which in this mode, memory is persistent. The device capacity is used as a byte-addressable persistent memory that is mapped into the system physical address space and directly accessible by applications. This is called DAX, direct access. Note that the device can also be configured in mixed mode, where a percentage of the DCPMM capacity is used in memory mode and the remainder in UpDirect mode. All of that introduction takes me to the actual topic today, which is to explore whether and how NVRAM can close the gaps that are introduced in high-performance computing systems. We focus on certain use cases that Optane may be beneficial and not on the raw performances of this new hardware. Moreover, we investigate whether new algorithmic approaches can be refreshed in order to much well suit this hardware. So let's continue by defining the settings and the problems we want to fix in regard to this to those settings. HPC typical setting for scientific computations goes like that. It usually consists of a large number of compute nodes that can communicate with each other with a network, for example, InfiniBand or Ethernet. A single calculation offer spans over a relatively large number of compute units, Each compute node consists multi-core processors and DRAM as main memory. The compute nodes have access to external distributed storage, and huge amounts of data should be analyzed and manipulated in main memory and stored in non-volatile memory. Running large simulations can take a quite long time. So recovery after failures may be very painful in complex systems that tends to crash frequently. That's why planning a computing system that can naturally provide efficient recovery to applications is imperative. One main way to deal with crashes is by storing checkpoints along the program's computation and recovering if a failure occurs. However, persisting huge checkpoints to standard storage devices is very inefficient. HPC simulations, which carries out their checkpoint restart functionality in conventional storage, suffer from a performance penalty for performing a checkpoint. So, can we somehow help in this regard? Secondly, the DRAM limitation. As of today, in order to support large computations, two common solutions can be applied. The first one is distributing the computation data to several compute nodes. These come with communication overheads, obviously. The second solution may be paging, which swaps the contents of to or from the primary memory with the secondary storage. This is very inefficient due to kernel engagement and high latency to storage access. Third, the storage weakness. Scientific computations often write and read huge amount of diagnostics and perform checkpoint restart with huge checkpoints. Since storage devices like a hard drive disk and solid state and flash are much slower than DRAM, they create a main bottleneck to the computation. This weakness harm the efficiency of checkpoints. So can we reframe the questions now and ask, how can we exploit NVRAM to improve scientific computations performances and fault tolerance in HPC systems? A hint would be that it's actually very simple and even could be done transparently. As the latency of obtained NVRAM is almost as fast as DRAM latency, obtained in memory mode may allow scientific applications to run larger problems, partially replacing the need for expensive paging or distributed the computations. The second way is for faster non-volatile storage, as we stated before in app-direct mode. In this mode, Optane provides persistency and allows byte-addressable access to non-volatile memory. With the usage of persistent memory-aware file systems, scientific applications may efficiently write-read diagnostics and also save and restore those checkpoints. So this is our suggested circle of NVRAM usages in common HPC systems. And we ask if this circle holds to the promise in regard to performances. We tested this hardware in the right setting using NAS and Polybench benchmark, representing the variety of HPC application domains, with great emphasis on the BT, the block diagonal, and CG, the conjugate gradient solvers. The beauty of BT solver is that it's simulating a computational fluid dynamics application. Its solution is derived by solving three uncoupled system of equations. The BTIO benchmark, its sibling, presents a block diagonal partitioning pattern and benchmarks the IO patterns used by the BT benchmark. The figure on the right shows an illustration of data partitioning pattern for 9 MPI processes. And we choose to focus on BT and BTIO as they exhibit patterns of massive communication between processes and intensive I/O. To evaluate obtained benefit in this use case of memory expansion, we perform the execution of scientific benchmark with increasing memory usage beyond the DRAM capacity. To evaluate the obtained benefits in this use case, we perform the execution of an IO-intensive scientific benchmark to evaluate the performances of obtained for reading and writing diagnostics. And to evaluate obtained benefits in this use case, we perform the execution of scientific benchmark with checkpoint restart. We persist the state of the computation along the program's computation to the obtained non-volatile memory and read back after a crash occurs. We consider external checkpoints, checkpoint restart, as well as internal, as will be explained shortly. Our experimental environment in this work consists of a single computation node having 2 sockets. Each socket contains a multi-core processor of 10 cores. The entire node contains about 200 G of DDR4 DRAM and 1 terabyte of obtained DCPMM. The right figure describes the memory population of the entire node. Each socket has 6 DIMMs of DDR4, each of 16 gigabytes, and 2 DIMMs of DCPMM, each of 256 gigabytes. We know that there are several ways to arrange the DIMMs, and according to several previous work, these different arrangements of DIMMs can affect performances. However, we did not deal with this issue and take this specific arrangement as given. Now, back to the first use case that we suggested. For this use case, of the main memory expansion, we executed some representative benchmarks from the polybench suite. These calculations are taken from linear algebra, data mining, stencil computations, and we executed the computations twice. Firstly, we've obtained in-memory mode to expand main memory, and secondly, we've swapped into a local SATA SSD device to support large virtual memory. The x-axis stand for the memory usage, and the y-axis stand for the performance in terms of floating point operations per second. And the calculation were limited to the resources of 1 socket. The dashed vertical lines on the graph represent the DRAM limit, which is about 100 G, the DRAM capacity of 1 socket. To generate different memory usage size, the size were changed manually in code. As can be seen in the results, before crossing the DRAM limit, performance are approximately constant in both graphs. When DRAM limit is crossed, performance decrease only by a factor of 2 to 3 when using obtained for primary memory extension, while they deteriorate by 2 to 3 orders of magnitude when using memory swap into local SSD. The NAS suite was also executed on our experimental environment, this time spanning the whole node's DRAM. We executed different problem sizes, and as well as in Polybench, computations of NAS that fit into the DRAM leads to quite the same results in both graphs, with approximately constant performances. After passing the DRAM limit, however, the performances decreases in the same pattern we observed with Polybench. So, obtained memory expansion enable running much larger problem sizes with the expense of only a few factors of increase in performance penalty. Now, let's talk about the second use case of fast persistent storage for scientific applications. We focus on ways to use the NVRAM in the most convenient and encapsulated ways. So no massive changes have to be inserted into existing scientific codes. Persistent memory file systems meet these requirements and provide applications direct access to non-volatile memory. Those PMFSs support a special mode called DAX, direct access, that enables memory mapping directly from the NVRAM to the application memory space. This bypasses the kernel, the page cache, I/O subsystem, avoids interrupts and context switching, and allows the application to perform byte-addressable load store memory operations. For the second use case of reading and writing diagnostic, we examine PMFS SplitFS, NOVA, and X4DAX with the BTIO benchmark. The following graph shows the result of BTIO with MPIO write workloads. The x-axis stands for the total I/O amount in gigabytes, and the y-axis stands for the bandwidth in megabytes per second. The orange trend shows the bandwidth of writing to a local SATA SSD device under the XFS file system, which the other trends show the performance of writing to Optane under SplitFS, NOVA, and X4DAX. We also modified BTIO to execute a file sync after every write to ensure the immediate transition of data to the Optane and SATA SSD. And the results show an improvement of 3 to 4 factors of I/O performances when using Optane DCPMM in respect to SSD. The graph show the results of BTIO with MPIO read workloads. We observe an improvement of up to 10 factors in read workloads performances with the Optane. The conclusion is pretty clear, and is that Optane DCPMM dramatically increase I/O operations as a fast local storage for scientific applications. For the third use case, to evaluate the performance of checkpoint restart with NVRAM, we introduced transparent and explicit checkpoint restart to the BT benchmark from NAS benchmark. And there are two ways to do so, either using DMTCP or SCR, and we will exhibit the two fashions. We applied the transparent and explicit checkpoint restart to the BT solver of NAS as we just saw, and in the explicit checkpoint restart case, at the end of each iteration of the computation, we persist the benchmark state. That includes matrices, the iteration ID, and some auxiliary data. And in the transparent checkpoint restart case, for a fair comparison, we implemented a DMTCP plugin that synchronized the checkpoint execution at the end of each iteration. We applied both DMTCP and SCR checkpoints to local SATA SSD device and to obtain DCPMM. The right graph shows the storage utilization of DMTCP and SCR checkpoints in an increasing number of processes. As expected, when using DMTCP, the storage utilization is greater, about 2.5 times than that of SCR, as the checkpoint of DMTCP involves more information. The left graph shows the runtime of BT in a crash-free computation. The blue line is for the original BT execution with no checkpointing. And the orange and green lines represent the runtime when conducting checkpointing to SSD using DMTCP and SCR, respectively. The red and purple lines represent the runtime with checkpointing to the Optane using the DMTCP and SCR. And the results show that both SCR performs better than DMTCP, but both perform better on NVRAM than on SSD. The middle graph shows the computation time in per iteration perspective. Each column presents the breakdown of recovery, checkpoint, and compute time in a single crash computation. The red part is for the checkpointing stage, the blue part is for recovery, and the brown for the iteration computation. As the results show, checkpoint restart on top of NVRAM shows shorter checkpoint duration both on DMTCP and SCR. And in addition, SCR demonstrates faster checkpointing and recovery durations compared to BT DMTCP. And by that, we completed the circle of NVRAM use cases in HPC completely. That's great, right? I mean, while we saw all the use cases in a single HPC node, we know they hold for distributed ones also, as Darrow's NVRAM system just kicked in, and other work by, for example, Patil et al. Show the efficiency of the memory expansion for many HPC computations. And you would assume, as I just said, that this is great, but it's not really great. As we all just saw, that reducing the fault tolerance checkpoint restart overheads, not actually eliminating them at all. So the big elephant in the room remains. That's why we change our focus to NVRAM utilization with algorithm-based fault tolerance to solve this problem once and for all. In order to support this fault tolerance from the inside, we need to know well what exactly we are facing. Well, not surprisingly, mathematics solvers account for about 50 to 90% of scientific applications operations. Specifically, linear iterative solvers are main kernels in scientific computing, especially when direct methods are expensive or do not exist. Distributed version of iterative solvers allow solving large problems on several compute nodes concurrently. Trilinus is an example for a collection of reusable scientific software libraries, including linear iterative solvers. Trilinus support the major parallel architectures, including distributed implementations with MPI. Fault tolerance solvers in Trilinus was investigated at Sandia and are enabled by selective reliability, which makes effort to make these solvers less sensitive to faults. This emphasizes that many efforts are made to support fault tolerance to iterative linear systems, so these solvers can be executed reliably on future exascale systems. Reviewing now the main mechanisms that support fault tolerance in iterative solvers, we already mentioned checkpoint restart, but let's go and review it again for this comparison. So checkpoint restart is used to persist the state of the solver to a storage every certain period. When failure occurs, this data can be retrieved back to memory and computation can continue. The advantage of checkpoint restart mechanism is that the state is read back after failure, and the solver can continue immediately without any reconstruction stages. However, frequent checkpointing, especially of the full state of the solver, is expensive, especially if executed with I/O calls to standard disk. Other mechanisms take advantage of increasing convergence features of iterative linear solvers. These methods do not persist large amount of recovery data. Rather, they assume that the solver can naturally recover from faults and make up for the lost accuracy. However, it might require extra iterations to converge and make up for the lost calculations. As you can see in the graph, the blue and green lines represent the quality of the PCG solver results when certain faults incur. Now let's talk about exact state reconstruction techniques. In short, ESR. ESR is an algorithm-based fault tolerance mechanism that provides exact state reconstruction of the computation after failures without the need of checkpointing the full state. Specifically, in-RAM ESR techniques creates certain level of redundancy to only some state variables by keeping their copies on the RAM of other nodes. When failure occurs, even if on several nodes simultaneously, the copies can be read back from the neighbors and the other state variables are reconstructed by local calculation. In this work, we found interest in the previous work of Chen that introduced an in-RAM ESR techniques for linear iterative solver. This method applies to iterative solvers that involve sparse matrix vector multiplications, in short SPMV. This technique utilizes the transference of values between nodes as part of SPMV operations. This naturally creates redundancy to any vector that participate in an SPMV operation. However, to support the recovery from a failure of C simultaneous nodes, C+1 copies should be made on different nodes. Because if C arbitrary nodes fail, we need to ensure that we still have an available redundancy for each process. That's why the SPMV operation is augmented to what is called a SPMV to create enough redundancies. In case of a failure, each failed process collects its redundancy from the other survived nodes and uses this recovery data to reconstruct the entire state on a replacement node. And then they continue the computation. 2 years ago, Pachajoa presented a generic strategy to create ESR for various linear iterative solvers. He presented a state reconstruction meta algorithm that can be applied to produce ESR algorithm for sensitive solvers, for example, the conjugate gradient method. However, in-RAM ESR has limitations. First, the memory footprint of the recovery data increases dramatically with the number of nodes. As the size of the problem increases with number of nodes in weak scaling, and the number of copies increases also with number of nodes, we get quadratic memory overhead. And since the DRAM is an expensive resource, we need to find ways to eliminate this overhead. Moreover, the transference of these copies between different nodes bring to dramatic time and networking overheads. Finally, as this method relies on DRAM for recoverability and does not rely on NVRAM hardware at all, this is a disadvantage for the next supercomputers that will integrate NVRAM. But before we dig into our solution, let's present two main architectures that include NVRAM. In the homogeneous NVRAM cluster, each compute node is equipped with its own node NVRAM cards connected directly to the CPU bus. This architecture is relevant, for example, in supercomputers that integrate NVRAM on node for main memory expansion, and also relevant in cloud HPC computing when the goal is to equip each compute node with as much memory and compute resources as possible. The second architecture holds the NVRAM on remote subcluster on dedicated nodes. This architecture is relevant, for example, in Aurora, when the DEOS storage system consists NVRAM outside the compute nodes. So in this work, we use the NVRAM to enhance the capabilities of exact state reconstruction techniques. In the model we called in-NVRAM ESR, the SPMV redundancies are persisted to NVRAM only once at each persistent iteration, instead of creating several copies and being transferred to the RAM of other nodes. As in RAM ESR, a persistent iteration can be applied every certain period. The reconstruction stage of in-NVRAM ESR depends on the cluster architecture. For the homogeneous cluster, if node fails, we need to wait until it recovers so we can access its persistent data and reconstruct the computation. In the subcluster architecture, when compute node falls, we can retrieve its recovery data from the remote NVRAM and reconstruct the computation on another spare node. To implement in NVRAM ESR, first for the homogeneous NVRAM cluster, we use the persistent memory development kit, the PMDK. Specifically, we create persistent memory object to each vector we want to persist with the libpmem_obj library, and we store this object on allocated pools on the byte-addressable NVRAM. To implement in NVRAM ESR for the remote NVRAM subcluster, we use an extension of one-sided communication in MPI that enables direct access over RDMA to NVRAM. This method is implemented with the post-start complete wait synchronization protocol by invoking an access epoch on the compute ranks and invoking an exposure epoch on the target ranks. Each architecture has its own pros and cons. In the homogeneous NVRAM cluster, persistency is local, so there are no network overheads or surge on a subcluster. However, if a compute node fails, we need to wait for its recovery before we can continue. In the remote NVRAM subcluster, however, we might experience networking overheads for accessing the remote subcluster. In addition, the NVRAM subcluster is a single node and a single point of failure in that case. Although this issue can be solved with raiding of the NVRAM nodes. Main advantage of the remote subcluster is when node fails. And then the computation can be reconstructed on a spare node that accesses the recovery data from the remote NVRAM. Now, let's see an example of in-NVRAM ESR for the preconditioned conjugate gradient solver. According to ESR technique, in the in-RAM ESR method, redundancies are made to the conjugate direction P and are sent to other compute nodes RAM during the computation. In our version of in-NVRAM ESR, we persist the values, in this case, the variable P, to the NVRAM only once at each persistent iteration, locally or remotely. And it is really that simple. Now, let's talk about the results of this change. The left graph presents for each number of processes how the RAM usage is partitioned into the computation itself and for recovery overhead. You can see that in NVRAM ESR does not incur any overhead of RAM for recoverability. Because we have only 256 processors on our system, we can simulate only that number of compute nodes. So we executed in-RAM ESR at the stress case of alpha equals 1 and alpha equals 0.5, which means copies are sent to all of the processors or only half of them, respectively. This helps us to simulate memory overhead in extreme cases that would appear in larger systems. The right figure shows that NVRAM usage increases in linear fashion when problem size increases, as we keep only one copy in NVRAM. We now measure the time overhead for a single persistent iteration. To simulate the homogeneous cluster, we have only one node containing NVRAM with 20 cores. We consider persistent to NVRAM via certain means, via local persistent memory fast system in green line, via PMDK as described before in orange, and via a local MPI window in pink. We also compare the results with persistent to local SSD device, which appears in red. Note that the vertical axis is in log scale, and the results show that writing to NVRAM with persistent memory file systems may be more efficient than creating pools with PMDK, but still more efficient than writing to SSD. The horizontal lines present the extrapolation of these simulations to several NVRAM compute nodes. Because the persistent operation is local and is executed in inversely parallel fashion, we keep the penalty constant. The in-RAM ESR time overheads, however, presented here for alpha equals 1 and even 0.1 increase dramatically. To estimate the time overhead in the remote NVRAM subcluster, we simulate in NVRAM ESR at up to 256 nodes in blue line. For reference, we considered also persisting the recovery data to remote SSD in black. The azure lines is for reference and present the time penalty of transferring the recovery data to remote window on RAM. And it is very interesting to extrapolate these results up to 9,000 compute nodes, which is the number of compute nodes in an actual exascale system, such as Aurora. We estimated in NVRAM ESR to be much more efficient than in RAM ESR in larger systems. As we extrapolate the results to Aurora supercomputer, we want to remind that while Aurora had 9,000 compute nodes, it also had about 10 petabytes of main memory. And the DAO storage that is being used with Aurora contains about 230 petabytes of storage, including NVRAM. Extrapolating the memory overhead of in-RAM ESR, we get up to 3 petabytes overhead for alpha equals 1 and 300 terabytes for alpha equals 0.1 for a computation that occupies the entire system. In-NVRAM ESR can reduce this overhead to 300 G on NVRAM, eliminating DRAM overheads for recoverability and leaving free the DRAM, what can enable executing large problem. And by that, we finally completed our introduction of NVRAM to HPC and supercomputing efficiently. To conclude, we can say that in this research, we investigated first if NVRAM can be helpful for HPC use cases. And we said that this is true. We get increased resolution and reduction of storage overhead. We asked how to utilize NVRAM transparently for HPC. We do so with memory increase. We do so with persistent memory file system, with checkpoint restarts. We asked whether supercomputers can enjoy those benefits, and we showed that they do using MPI windows, efficient PMDK, DEOS PMFS, and so forth. And we also asked what it takes to increase fault tolerance algorithmically. And we focused on iterative solvers, on algorithm-based fault tolerance, and on our novel technique, which we called in-NVRAM ESR. For discussion, obviously, there are some other questions. We asked whether we can reduce the effort of doing those ESR implementations algorithmically somehow by automation. We also asked, what about direct solver? We only focused on iterative solvers. We asked about other data structures, not actually talking about an array. And obviously, the big elephant in the room is the future of Intel Optanes, which just been discontinued. But as we see in the news, we will eventually get some sort of new NVRAM in the future. So hold tight. And by that, I would like to thank you, everyone.